Every jackup rig actually lives two completely different lives. First, it's a boat navigating the harsh ocean, and then it transforms into a massive, fixed skyscraper standing high above the waves. Today in this explainer, we're diving into the anatomy of the Cat J jackup rig, specifically looking at its hull and legs.
Okay, let's dive right into this. As I mentioned, a rig like this has two operational states. It floats like a buoyant barge, so it can be towed to a location, and then it literally jacks itself up to become a fixed platform on stilts. And the stakes here? They are absolutely immense. Because if engineers get this state change transition wrong, you either can't float the rig out there in the first place, or you can't lock it down safely once it arrives. It's a catastrophic failure either way.
So here is our game plan for this explainer. We'll start with the two lives, then dismantle the anatomy of this megastructure top to bottom. We'll look at the hull, the lattice legs, something called the operational air gap, do a quick check on the engineering, and finally wrap it up with a summary.
Section 1. The two lives.
Now the Cat J class, and specifically the Gusto MSC CJ70 design, exists for a very specific reason. The North Sea absolutely punishes anything that floats. So this rig has to function flawlessly as a towable boat, but then it uses its colossal legs to lift itself entirely out of the water. The ultimate goal here is that a violent storm, one strong enough to literally capsize a supply boat, could be raging right underneath, but the driller working on the floor up top, they feel absolutely zero motion. It's locked in securely.
Section 2. The hull. Giant buoyant steel box.
So, the hull. This is the watertight structure that actually gives the rig its buoyancy during transport. To put the scale into perspective, it's roughly 297 feet long, 378 feet wide, and nearly 40 feet deep. It's basically a gigantic steel box. It provides that essential buoyancy when it's being towed, but once elevated, it becomes the solid foundation for literally everything on board. We're talking heavy drilling machinery, massive mud systems, and all the living quarters.
And this brilliantly illustrates just how massive that scale is. Looking at the Askeleton, which is a sister rig in the Cat J class, you realize this isn't just a platform. It is a self-contained miniature city in the middle of the ocean. It supports 120 to 140 crew members right alongside thousands of tons of heavy industrial equipment. You know, if you look closely, you'll see how the accommodation block wraps entirely around that forward leg. That gives the living quarters structural shielding and intentionally keeps the crew as far away from the hazardous drill floor as physically possible.
Section 3. Lattice legs. Triangulated strength. 214 meters. Just let that number sink in for a second. That is the length of each of the rig's 3 legs. At roughly 700 feet, they're taller than the Space Needle in Seattle. These massive stilts have to reach all the way down to the seabed, plant themselves firmly, and then hoist that entire floating city we just talked about straight up into the sky.
Now what's really interesting about this slide is the structure itself. Notice how these 700-foot legs aren't just solid steel tubes. They are these towering, intricate lattice structures utilizing what engineers call X-bracing between the outer leg cords. They're actually designed to resist extreme bending loads from the ocean, exactly the way a heavy-duty crane boom works. It is such a fascinating engineering solution. By using that triangulated bracing, the design takes those terrifying bending forces caused by crashing waves and high winds, and it just converts them into simple tension and compression along the individual steel members. This specific geometry gives you maximum structural strength while saving an enormous amount of weight compared to building a solid structure. And honestly, that weight saving is absolutely critical when you're dealing with 3 legs that are each over 200 meters long.
Section 4. The operational air gap.
69! So why 69 meters? Well, once elevated, the rig maintains this 69-meter operational air gap between the underside of the hull and the mean sea level. This is your ultimate safety buffer. The rule of thumb here is that the air gap requirement must equal the maximum expected wave crest height for a 100-year storm plus an extra safety margin because, let's face it, the ocean is always trying to prove engineers wrong. If the calculated air gap can't clear this strict rule, the rig cannot safely jack up at that location. Hard stop, no exceptions.
Section 5. Quick check. Why lattice legs?
Okay, quick check. I want you to ask yourself this. Why not just build those giant legs as solid steel columns? I mean, intuitively, surely a thick, solid pillar of steel would be much stronger than a see-through lattice truss, right? Let's actually consider the physical consequences of swapping out that triangulated framework for a solid steel pillar. Well, here's exactly why that wouldn't work.
A solid steel column strong enough to match the capacity of a lattice leg would weigh dramatically more, and when you multiply that massive extra weight across 3 legs, each 214 meters long, the physics just completely fall apart. All that extra weight would demand a significantly larger hull just to provide enough buoyancy to keep the rig from sinking into the ocean. You'd need more steel everywhere. Ultimately, a rig of this scale built with solid legs would be literally impossible to float and impossible to tow. The highly weight-efficient lattice design is the only thing that makes a megastructure this tall actually buildable.
Section 6. Summary and next steps.
Let's bring all this together. The real takeaway here is how the progressive scale of this megastructure works in perfect harmony. You've got the hull, a massive 297 by 378-foot floating steel box housing a miniature city. You've got the legs, those 214-meter triangulated lattice towers that provide incredible strength without the sinking weight. And you have the air gap, that 69-meter buffer ensuring the worst 100-year storms pass harmlessly underneath. All of these elements combined execute that flawless boat-to-skyscraper transition.
But I want to leave you with a provocative thought as we wrap up part 1. Today, we cover the hull and those massive legs suspending it high in the air. But what happens at the very bottom? Think about it. What happens when thousands of tons of steel resting on those 214-meter legs finally hit the soft, layered mud of the ocean floor? How do engineers prevent a catastrophic seabed collapse known in the industry as punch-through? It is a genuinely terrifying risk, and we're going to uncover exactly how they solve it in part 2. Thanks so much for learning with me today, and I'll see you in the next explainer.